Now, continuing to next topic, that is Kp problems in chemical equilibrium. So we'll understand the Kp, that is the constant for pressure, using this problem, and the problem is at 300 Kelvin and 1 atm, N2O4 is dissociated into NO2. What will be the percentage dissociation at 27 degrees centigrade and 0.1 atm pressure? So we have been asked by giving the dissociation at 1 atm, and we have been asked what will be the percentage dissociation at 0.1 atm. So let's continue the problem. N2O4's equilibrium equation would be like this: N2O4 dissociating into 2NO2, and as here been written that the dissociation is 20%. So let's say this was 1 minus alpha and 2 alpha would be formed. So we can say 2 alpha by 1 minus alpha plus 2 alpha would be the mole fraction of NO2. So it comes out to be 2 alpha by 1 plus alpha. And similarly, mole fraction of N2O4, it would be 1 minus alpha by 1 plus alpha. Why we calculated mole fractions was because we have to deal with pressure in the problem. So we can now write the Kp as 2 alpha by 1 plus alpha into total pressure P whole square divided by 1 minus alpha by 1 plus alpha multiplied by P. So by calculating and replacing P with 1, Kp comes out to be 0.166 atm. Now we will use this Kp to find out the percentage dissociation when the pressure would be 0.1 atm. So let's say degree of dissociation be beta, beta at 0.1 atm pressure. Because degree of dissociation is dependent on pressure, it will change at different pressure and temperature. So again, Kp will be the constant and it will not change. Kp would be 0.166 equals to 4 times beta square 1 minus beta square multiplied by P. P here is 0.1 atm, and we'll equate this to 0.166, and beta from here comes out to be 0.54. So the percentage dissociation would be 54%. And that's all about Kp problem. The important thing in Kp problems is you have to deal with mole fractions, because in case of pressure we find out the pressure of individual gases in the reactions using mole fractions of that individual gas. So that's all about Kp problem in chemical equilibria.